right now, in places like Plainview, Long Island, there are these heavy wooden shipping crates just being cracked open in these totally nondescript warehouses.
Yeah, it's happening every day.
And what is stepping out of those crates is, I mean, it's basically the opening scene of a science fiction movie. We are talking about highly advanced bipedal humanoid robots.
That's right. The kind of stuff we've been dreaming about for decades.
Exactly. And they cost less than a used Honda Civic. They can literally do backflips, and tech billionaires are just buying them by the thousands.
It's an absolute flood of hardware.
But, here's the catch. If you buy one of these machines right now, take it into your house and ask it to, open your dishwasher, it will completely crash its system.
Oh, totally. 100%.
And honestly, if you aren't paying attention, it might just break your toe in the process.
Yeah, it is a phenomenal contradiction to witness right now. Because you have this massive influx of imported robotic hardware arriving on American shores, right? And these machines, I mean, they look like they just walked out of a glossy tech presentation.
They look completely finished, like a consumer product.
Exactly. But the gap between the perception of a fully autonomous robotic helper, the kind that might actually do your laundry, and the physical reality of the metal and plastic being unpacked in Long Island right now, it is a chasm.
It's huge.
We're existing in this incredibly strange twilight zone where the mechanical future is technically here, standing right in front of us, but it requires a staggering amount of assembly.
Right, and an unfathomable amount of programming.
Yes. And on top of all that, it is raising some of the most serious cybersecurity questions of our generation.
Gee, as an engineer, I spend my entire day looking at the mechanics of the future, right? I'm looking at schematics, wondering how we piece the next 10 years together.
Sure.
But as a parent of 2 kids, I have a much simpler, much more desperate dream. I mean, I just want a robot that can load the dishwasher.
The ultimate holy grail of robotics.
Right. I want a robot that can pick up the Legos without complaining. And you, listening to this deep dive right now, have undoubtedly seen the viral videos on your feed.
Oh, well, they're everywhere.
The slick humanoid robots doing perfectly choreographed dances or jumping over obstacles or seemingly doing household chores. It really feels like we have finally crossed the finish line.
Well, that feeling is very intentional.
Really?
Those videos are meticulously crafted to evoke that exact sense of arrival.
Exactly. And that is the illusion we are tearing down today. Okay, let's unpack this. In this deep dive, we are going completely under the hood.
Let's do it.
We are going to look at the star of those viral videos, which is a Chinese humanoid robot called the Unitree G1, and we'll explore the stark, sometimes painful difference between internet hype and its actual capabilities when you pull it out of the box.
Yeah, the real out-of-the-box experience.
Right. And then we're going to examine the wild, highly tactile ways researchers in the U.S. are using virtual reality to physically teach these metal shells how to move.
And we really need to unpack the underlying strategy there, too, because it reveals a massive divide in the global tech ecosystem right now.
The separation between who builds the bodies and who builds the brains.
Precisely. The divide between the hardware and the software.
Great. And, you cannot bring thousands of heavy sensor-equipped machines with foreign-coded operating systems into top-tier American AI labs and living rooms without ringing. Every single cybersecurity alarm bell in existence.
It is a security nightmare.
It really is. So we will be looking at the very real, very physical threats these machines pose, how American competitors are desperately trying to build domestic alternatives, and why, despite all the security fears, the global robotics market right now is not a simple race. It's an incredibly complicated, intertwined dance.
Yeah, a complicated dance is the perfect way to put it.
So let's just start with the hardware that is flooding the zone right now, the Unitree G1.
Right. So if you have scrolled past a video of a humanoid robot in, say, the last 6 months, there is a remarkably high probability you were looking at the Unitree G1.
It's just everywhere online.
Exactly. Unitree is a robotics company based in Hangzhou, China, and they have successfully shipped more humanoid robots than any other company on the planet. And they have completely saturated the market.
And the reason they have saturated the market comes down to one number, right? $13,500.
Yep, that's the starting retail price.
Now, obviously, to you and me, 13 grand is a massive amount of money.
Right, that's a car.
That's a down payment on a house in some places. But in the context of advanced bipedal robotics, that is absurdly cheap.
Oh, it's practically free in the robotics world.
Yeah. Just a few years ago, a research university would have to spend $500,000 just to custom mill the parts, to build a bipedal prototype that could barely walk across a flat floor without tipping over.
And usually it's still tipped over.
Exactly. But the G1 is mass-produced, it's readily available, and the marketing is undeniably brilliant. I mean, they released a video for the Chinese New Year where a line of these robots performed a perfectly synchronized dance.
I saw that one. It was wild.
There are videos of them doing stage combat, but my personal favorite, because it is just so chaotic, is a video where they actually programmed a Unitree robot to chase a Polish boar through the woods.
Yes, the Polish boar video.
It looks incredibly capable. I mean, running through a forest, that's tough.
Well, it looks capable because we as humans are very susceptible to what is essentially an illusion of general intelligence.
What do you mean by that?
Well, when you see a robot navigating the uneven terrain of a forest while chasing a wild animal, your brain naturally extrapolates.
Oh, I see. You fill in the blanks.
Exactly. You automatically assume that if this machine possesses the dynamic balance, the gyroscopic stability, and, the processing power to not trip over a tree root while running, then it surely possesses the baseline competence to walk into a kitchen, pick up a sponge, and wipe down a counter.
Right, because to us, wiping a counter is much easier than running through a forest.
Right. But that is a fundamental misunderstanding of how robotic programming works.
Which brings us to the reality check, because someone actually decided to test that exact assumption.
Yes, they did.
A technology journalist recently acquired a Unitree G1, had it delivered to her house, and decided to see what it could do right out of the crate.
And how did that go?
Well, as a parent hoping for a robotic nanny, reading about her experience was completely devastating.
I can imagine.
She set it up in her kitchen and gave it a basic command. She literally just asked it to open the dishwasher.
Uh-oh.
Yeah. The robot stood there, processed the request, and its system literally replied out loud, "Please check the network and try again."
Wow.
It was entirely paralyzed by the concept of a dishwasher handle. She asked if it could cook? No. Could it do the laundry? Absolutely not.
And we really have to explain why it can't do those things.
Please do, because it's confusing.
The basic G1 model, the one that costs $13,500, is not an autonomous agent. Out of the box, it lacks the onboard compute.
The actual processing chips, right?
Yeah, the chips and the advanced neural network software required to make independent decisions in a complex, unmapped environment, like a human house.
Which is incredibly chaotic compared to a lab.
Exactly. So when you see it doing those impressive maneuvers in promotional videos, or even moving smoothly through a room in a demonstration, it is essentially acting as a highly sophisticated, incredibly heavy, remote-controlled car.
Wait, really? Like a literal RC car?
Literally. In the journalist's case, the robot came with a team of technicians holding a handheld controller to drive it around her kitchen.
I think this is where we have to introduce Moravec's paradox.
Ooh.
Because it perfectly explains why chasing a boar is somehow easier than foiling a t-shirt.
Yes, Moravec's paradox is crucial here.
As an engineer, I see this all the time. Moravec's paradox is this incredible observation in artificial intelligence that high-level reasoning, like playing chess or doing complex math, requires very little computation.
Right, a calculator can do that.
Yeah, we solved chess decades ago. But low-level sensoromotor skills, the things a 2-year-old child does instinctively, like recognizing a face, walking upstairs, or picking up a soft object without crushing it.
Those require enormous mind-boggling computational resources.
Exactly. Let's look at the physics of opening a dishwasher. To a human, it's a single thoughtless action. You just grab and pull.
But to a robot, it is a nightmare of physics and spatial reasoning.
Walk me through it. What is the robot actually dealing with?
Okay, first, the robot's vision system must identify the handle, right? Distinguishing it from the reflective stainless steel background of the kitchen.
Oh, right. The reflections would confuse the cameras.
Totally. Then it has to calculate the exact spatial coordinates of that handle in 3D space. It must move its arm, adjusting the torque in its shoulder, elbow, and wrist joints, using complex kinematic equations just to arrive at the handle without slamming into the door.
And then it actually has to grab it.
Yeah, it has to grasp the handle and apply exactly enough force to unlatch it, but not so much force that it rips the door off its hinges.
Which is hard enough, but then the door moves.
And here's the hardest part. As it pulls the door down, the door moves in an arc.
Right.
The robot must continuously adjust its grip and dynamically shift its own center of gravity backward so that the shifting weight of the door doesn't pull the robot face first onto the kitchen floor.
That is insane when you break it down like that.
Yeah.
And the $13,000 base model of the G1 simply does not have the brain to process that dynamic shift.
No, it doesn't.
It has the motors, it has the metal joints, but it is effectively blind and mindless without a human operating the joystick.
Exactly.
And that creates a massive safety hazard. I mean, we aren't talking about a Roomba bumping into your baseboards. We were talking about bringing entry-level bipedal heavy machinery into domestic spaces.
And the journalist experienced this firsthand, didn't she?
She did. While they were testing the robot, the operator on the joystick made a slight miscalculation. The robot took a step, brought its heavy metal foot down directly onto the journalist's toe, got stuck there, and literally broke her toe. Yeah. She didn't even see it coming.
You know, that broken toe is the perfect visceral metaphor for the current state of consumer humanoid robotics.
How so?
Well, you have powerful actuators, the motors that drive the joints, that are capable of delivering massive amounts of force.
Right, they have to be strong to carry their own weight.
Right. But the basic shell lacks localized force feedback sensors that would tell it, hey, there is a soft human foot under my metal foot. I should stop applying downward pressure.
It just blindly follows the joystick.
Exactly. It just executed the mathematical command sent from the joystick, move foot to XYZ coordinate. Didn't know a toe was in the way.
So we have a machine that has zero spatial awareness, is being driven blind by a human on a joystick, can't open a dishwasher, and will break your bones if it steps on you.
Yeah, that's the reality right now.
I look at this and I have to ask the obvious question. I'm looking at this price tag and it hits me. The smartest people in tech, the engineers at OpenAI, the researchers at MIT, they aren't buying thousands of these things because they want a remote-controlled toy.
No, definitely not.
They're buying them for a completely different reason.
They are buying them because they are looking at the math of hardware development.
Okay, unpack that. What's the math?
Developing bipedal robotic hardware from scratch is brutally expensive and time-consuming. You have to design custom harmonic drives, which are the specialized gears used in robotic joints.
Which are incredibly hard to manufacture.
Very hard. You have to design the motor controllers, the battery management systems, the structural chassis. If you are a software developer at an AI company in Massachusetts, your expertise is writing code, not milling aluminum.
Right, you don't want to reinvent the wheel.
Exactly. So when a company in China offers you a fully assembled, highly articulated, incredibly durable physical platform for less than $14,000, you don't care that its onboard software can't do laundry.
You just want the body.
You are buying the empty shell. You're
Yeah.
buying the body, so you can hollow it out, bypass its basic systems, and build your own advanced AI brain to put inside it.
Which means the warehouse in Long Island isn't the final destination at all.
No, places like RoboStore are just a waypoint.
Right. Once these G1s and other imported models arrive, they are being shipped directly into the most advanced research environments in the country.
They're going straight to the labs.
Yeah, they're going to artificial intelligence labs. They're going to university campuses. Like MIT is heavily involved in testing these machines in simulated medical settings.
And NVIDIA, too. They're huge in this space.
Yes, NVIDIA. And the ways these American researchers are treating these imported metal shells is fascinating. They are essentially treating them like physical infants.
It's true. They really have to start from zero.
They are putting them through a rigorous, almost bizarre training regimen to teach them how to interact with the physical world.
The term for this in the field is imitation learning. And it is a massive shift in how we think about programming.
How did we do?
Well, historically, if you wanted an industrial robot arm on an assembly line to weld a car door, you wrote thousands of lines of explicit code. Move joint A, 45 degrees, wait 2 seconds, fire welder. Move joint B, 10 degrees.
Very rigid step-by-step instructions.
Exactly. That works in a perfectly controlled, predictable factory environment. But a human living room is not predictable.
No, not at all. Especially with kids.
Right. Chairs get moved, toys are on the floor, lighting changes. You cannot explicitly code a robot to handle infinite unpredictability.
So what's the alternative?
Instead, you have to teach it the way you teach a human, by showing it.
And the primary way they're showing these robots how to move is by using virtual reality.
Yeah, the VR setups are incredible.
If you've ever played a VR video game, you understand the basic concept, but the application here is wild.
It's full telepresence.
Right. A human researcher puts on a high-end VR headset and holds motion-tracked controllers. The headset is wirelessly linked to the robot's camera system.
So they see what the robot sees.
Exactly. When the researcher looks left, the robot's head physically turns left, and the researcher sees what the robot sees in real time.
But it goes way beyond just vision.
It's full teleoperation. The researcher reaches out their arm in the empty air of the lab, and across the room, the heavy metal robot mimics that exact movement.
Like a high-tech puppet.
Yeah. They use this setup to perform tasks, picking up a cup, opening a door, sorting objects.
And as the human performs the task through the robot's internal computer is recording a massive stream of what we call kinematic data.
Kinematic data, what exactly is that?
Kinematic data is the pure geometry and physics of movement. It is recording the exact angle of every single joint at every millisecond.
Oh, wow.
It is recording the velocity of the arm swing. It is recording the torque, the rotational force applied by the motors when the robot's hand makes contact with a surface.
So it's translating the physical world into numbers.
Exactly. It is translating the physical, tactile world into a mathematical data set.
But VR isn't the only way they are generating this data. There's also a highly tactile physical teaching mode, right?
Yeah, the compliance mode.
The journalist who broke her toe actually got to demonstrate this before the accident. You can switch the robot into a compliant state where the motors basically disengage their rigid hold.
They go limp, essentially.
Right. And you can physically grab the robot's metal limbs like a giant puppet. The journalist grabbed the robot's arms and manually pressed its hands down onto a table, pushing them back and forth to mimic a wiping or scrubbing motion.
Which is such a wild image to think about.
It really is. And while she was doing this, physically moving the heavy metal arms, the robot's onboard system was audibly announcing, "Learning! Learning!"
See, training physical AI without kinematic data is like trying to teach someone to swim by having them read a textbook on fluid dynamics.
That's a great analogy. They have to get in the water.
They need to feel the water. When the journalist pushes the robot's hand onto the table, the sensors in the robot's joints are recording the resistance. They are recording the friction of the table surface.
And all that data goes where?
This data is fed into a neural network. Through a process called reinforcement learning, the AI analyzes thousands of these recorded human demonstrations.
Thousands of them just for wiping a table.
Thousands. Eventually, it builds an internal model of physics. It learns that if it applies X amount of downward force while moving laterally, it will successfully wipe the table without pushing the table over.
Wow.
The more data you feed it, the more generalized its understanding of the physical world becomes.
Here's where it gets really interesting. I look at this process, American engineers putting on VR headsets to puppeteer Chinese-built robotic bodies, and it illuminates the central divide, the grand strategy of the entire global robotics industry right now.
The massive split between hardware dominance and software innovation.
Exactly. Right now, China has an undeniable, overwhelming advantage in hardware manufacturing.
No question about it.
They have the supply chains, they have the subsidized raw materials, and they have the industrial capacity to mass produce complex mechanical systems at a price point that the United States currently cannot touch.
$13,000.
Right. But the U.S. companies are making a very calculated bet. They're betting that the hardware is ultimately a commodity.
It is a profound calculation. The American thesis is that the physical motors, the harmonic drives, the battery packs, these are just the plumbing.
It's just the vessel.
Right. The true value, the trillion-dollar prize in this industry, is the artificial general intelligence, the software brain that will eventually pilot the machine autonomously.
So they're seeding the hardware race, in a way.
Yes. The U.S. is essentially saying, let China build the bodies, we will buy them cheap, use them to harvest kinematic data, and we will build the brain.
It feels like an exact replica of the consumer electronics dynamic we've seen for the last 2 decades.
How do you mean?
Look at the iPhone in your pocket or the MacBook on your desk.
Yeah.
We view those as premium American products. The operating system, the user interface, the overall design, and crucially, the incredibly advanced silicon architecture.
The chips.
The logic chips designed by Apple or the AI processors designed by NVIDIA, those are born in California.
Right.
But the actual physical assembly, The mining of the rare earth metals for the battery, the stamping of the aluminum chassis, the soldering of 1,000 microscopic capacitors onto the motherboard.
Labs overseas.
Exactly. That relies almost entirely on vast, highly specialized manufacturing hubs in Asia. Foxconn builds the phone, but Apple owns the ecosystem. American robotics companies are trying to replicate that model.
They are, but
Mhm.
there is a critical distinction that makes robotics fundamentally different and much more problematic than smartphones.
What's the distinction?
An iPhone is a closed, static system. It sits in your hand. A
Mhm.
humanoid robot is a mobile, heavy, kinetic machine that physically interacts with this environment.
Walks around your house.
Exactly. And because the hardware and software must be perfectly seamlessly integrated to prevent the machine from, say, crushing your foot or walking through a plate glass window, you cannot simply slap an American software brain into a Chinese hardware body without deep, intricate communication between the two.
They have to talk to each other constantly.
Constantly. And that required communication is exactly what opens the door to the most terrifying aspect of this entire technological leap,
The security risks.
the security risks.
If you've ever set up a smart home device, like a doorbell camera, a thermostat, or a smart speaker, you know how annoying the network permissions can be.
Oh, it always wants everything.
Right. It wants your Wi-Fi password, it wants access to your local network, it wants to connect to a cloud server to download firmware updates.
Right.
Now, take that concept and attach it to a 100-pound bipedal machine equipped with sensors that make a smart doorbell look like a child's toy.
It's a completely different scale.
When we talk about bringing these machines into U.S. labs, universities, and eventually homes, we are talking about importing highly mobile, autonomous sensory platforms.
We really need to detail exactly what kind of sensors we're talking about because it contextualizes the security threat.
Please do. What is on these things?
To maintain dynamic balance and navigate a chaotic environment, a humanoid robot requires an array of advanced sensors. It has stereoscopic high-definition cameras in its head to provide depth perception.
Okay, so it sees in 3D.
Yes. It likely has LiDAR light detection and ranging which pulses lasers millions of times a second to create a hyper-accurate, millimeter-perfect 3D topographical map of its surroundings.
Wow.
It has ultrasonic sensors to detect glass or transparent surfaces that cameras might miss. It has highly sensitive microphone arrays to detect voice commands and localized sound. It has gyroscopes, accelerometers, and thermal sensors.
So when this robot is walking around an MIT medical testing facility or pacing the halls of an OpenAI development lab or standing in your living room while you eat dinner, it is not just existing in that space.
No, it is actively ingesting it.
It is building a real-time, three-dimensional, high-fidelity map of the architecture.
Yes.
It is capturing the audio of the conversations happening around it. It is logging the Wi-Fi networks in range. It is absorbing an ocean of data every single second just to function.
And this brings us to the security research that completely changes the tone of this conversation.
Yeah, the independent audit.
Right. Independent cybersecurity researchers recently got their hands on an imported Chinese humanoid robot and subjected it to a rigorous security audit.
And what did they find?
What they found wasn't just a minor bug or a glitch. They found catastrophic vulnerabilities.
Oh, man.
The researchers identified two major critical security flaws. The first was an alarming lack of encryption and authentication protocols in the robot's internal network architecture.
Meaning what exactly?
Meaning, it essentially allowed for a complete remote takeover of the machine's motor functions by an unauthorized user.
So anyone could just log in and drive it.
If they found the exploit, yes. But the second discovery, however, is the one that truly alarms the intelligence community. They found an active phone-home data logging mechanism.
Let's explain what phoning home means in this context, because it sounds somewhat innocuous, but it is a massive red flag.
It really is.
When a device phones home, it means the hardware has embedded firmware or software that is programmed to automatically package up the data it collects.
All that LiDAR and audio data.
Right. In this case, the telemetry, the logs, potentially the spatial maps and visual data, and transmit it over the internet back to a remote server controlled by the manufacturer.
Which, in this case, is overseas.
The researchers found that this robot was actively routing data back to servers located overseas.
And when looking at the security landscape, it's impossible to ignore the geopolitical tension surrounding that flow of data.
We have to talk about the espionage concerns. And just to be clear to the listener, we are impartially reporting the warnings from the source material here. We aren't endorsing a specific political viewpoint. We just want to convey the reality of what the intelligence community is saying.
Right, absolutely. We are talking about data exfiltration. The FBI and the broader U.S. intelligence community have been extremely vocal, publishing explicit warnings regarding economic espionage and counterintelligence efforts originating from the Chinese government.
They are taking this very seriously.
They view the systematic collection of American data, whether it is corporate intellectual property, medical records, or in this case, the detailed interior mapping of critical research facilities, as a grave national security threat.
It is a totally different paradigm than the tech bans we've seen recently. Look at Huawei smartphones, or the recent massive pushback against Chinese electric vehicles entering the U.S. market.
Right, the EV bans are a big deal right now.
Those technologies faced intense scrutiny, severe restrictions, or outright bans specifically because lawmakers and intelligence officials were terrified that they could be used as Trojan horses for data surveillance.
Exactly.
Yet somehow these humanoid robots, which collect exponentially more granular localized data than a car driving down a highway, are currently just walking right in through the front door of U.S. Customs.
Damian Shelton, the co-founder and chairman of Agility Robotics, which is a U.S.-based robotics company, has been very vocal about these exact fears.
What's his take on it?
He breaks the threat down into two distinct categories.
Yeah.
The first is the direct espionage risk, the literal exfiltration of sensitive audio, visual, and spatial data from secure U.S. facilities back to foreign servers.
Which is bad enough.
But his second point highlights a more subtle, long-term strategic threat regarding AI development.
Ah, the data advantage.
Yes, the data advantage.
In the world of artificial intelligence, algorithms are important, but data is the oxygen. The AI model that consumes the most high-quality, diverse training data almost always wins.
That's the golden rule of AI.
So, if a foreign entity has embedded access to the massive amounts of kinematic and environmental data being generated by thousands of robots operating inside the most advanced American labs, universities, and diverse domestic homes, that is an incalculable technical advantage.
They are essentially crowdsourcing their AI training data from inside American infrastructure.
Wow. So the American engineers puppeteering the robots in VR might be unwittingly training a foreign AI model simultaneously.
Exactly. But this raises an important question. The data exfiltration, as damaging as it might be from an intelligence or economic standpoint, is still a digital threat.
Right.
The unique terror of humanoid robotics is that it merges digital vulnerability with physical reality.
Yeah.
This is the domain of cyber-physical systems.
And as a parent, this is where my brain immediately goes. A hacked smartphone is a nightmare. It means stolen passwords, compromised bank accounts, leaked photos. It is a massive violation of privacy.
It's awful.
But a smartphone cannot physically assault me. A hacked 100-pound machine made of steel and powerful harmonic drives standing in my kitchen is a completely different risk profile.
It's a literal physical danger.
Security experts are floating this terrifying hypothetical. Imagine you have one of these robots in your home. It connects to your standard, easily compromised home Wi-Fi network.
Which is usually just a basic router password.
Yeah. A hacker, whether it's a state-sponsored actor or just a malicious individual, exploits a vulnerability, bypasses the authentication, and takes remote control of the system.
Because we know the G1 had that exact flaw.
Exactly. In the middle of the night, they decide to send a torque command to the arm actuators, directing the robot to pick up a heavy object, walk into your bedroom, and strike you.
It sounds hyperbolic, I know. Like a bad horror movie. But mathematically and architecturally, it is entirely plausible if the system lacks robust air-gap security.
It's just sending a command to a motor.
Exactly. When a cybersecurity failure crosses over from the digital realm into the physical realm, the consequences escalate from financial or reputational damage to potential lethality.
Because it's moving heavy metal around humans.
A digital buffer overflow exploit usually crashes a program. A buffer overflow in a robotic motor controller could send an actuator spinning at maximum velocity into a human being.
Which would break bones easily.
The experts emphasize that any time you connect a device to a cloud server, you are extending a sphere of vulnerability. You are opening a door.
And attaching that door to a 100-pound robot.
When you attach that open door to a machine capable of exerting significant physical force in a domestic environment, the stakes are exponentially higher than a hacked smart thermostat turning up the heat.
So, if the stakes are potentially lethal and the data theft risk is massive, how on earth are American companies defending against this? I mean, they are actively buying this hardware, so they must have a mitigation strategy.
They do, and it starts with the distributors.
The distributors handling this influx, places like the Robo Store in Long Island, aren't just taking the crates off the boat and shipping them blind to MIT.
No, they are executing what the industry calls the black box approach.
How does that work?
They unpack the robots, disassemble parts of them, and actively attempt to lobotomize the machines.
Lobotomize them.
Yeah, they try to strip out the native Chinese operating systems and proprietary software. They advise their American clients to use the robot purely as a dumb terminal, like a mechanical puppet.
Just bypassing the brain entirely.
They force the robot's networking hardware to communicate exclusively with US-based cloud platforms like Amazon Web Services, entirely cutting off access to any deep-routed networks that might lead back to foreign data centers.
So the intention's to build a firewall. The American developers are saying, I am going to take your impressive hardware, wipe its brain, install my own secure custom firmware, run it exclusively on my closed encrypted local network, and therefore I have neutralized the security threat.
That's the pitch, yes.
But as an engineer, I hear that mitigation strategy and I immediately see the massive glaring holes in it.
Oh, there are huge holes.
Wiping a laptop hard drive and installing a fresh copy of Windows is a relatively straightforward process. But a humanoid robot is not a laptop.
No, not at all.
It is not a single hard drive and a single processor. It is a deeply complex, incredibly convoluted network of dozens of microcontrollers. Every single joint, every camera module, the LiDAR scanner, the battery management system, they all have their own proprietary firmware baked into the silicon at the factory.
That is the absolute crux of the hardware security dilemma.
You cannot just wipe a robotic system of that complexity with a USB drive.
Right. A malicious backdoor or latent data logging protocol does not need to reside in the high-level operating system that the American developers are replacing.
It could be hiding anywhere.
It could be hard-coded into the low-level firmware of a motor controller chip. It could be hidden in the image processing logic of the stereoscopic cameras.
And you'd never know.
If a foreign manufacturer wants to retain a backdoor, they embed it deep in the component architecture. To find it, you would have to perform a microscopic destructive security audit.
Which means destroying the robot.
Yes. You would have to desolder chips, reverse engineer proprietary, undocumented code, and physically destroy the hardware to verify its integrity.
You can't do that to a $13,000 machine you just bought to use.
Because doing that to every single robot is economically and practically impossible, you arrive at a sobering conclusion. You can never, ever achieve 100% trust in imported hardware.
And it is precisely that fundamental inability to trust the imported hardware that is lighting a fire under the domestic robotics industry.
Yeah, the U.S. competitors are moving fast.
The United States isn't just relying on hollowing out Chinese robots and hoping they caught all the spyware. There is a massive multi-billion-dollar race to build homegrown, fully American humanoid alternatives from the ground up.
We are seeing incredible pushes from several major companies.
Let's name them. We have Agility Robotics, which builds a highly capable, slightly bird-legged robot called Digit, specifically designed for warehouse logistics.
Right. Digit is already moving boxes.
There is 1X Robotics, building models like Eve and Neo. There is Figure, a company that recently partnered with OpenAI to give their Figure 01 robot the ability to literally have a conversational, reasoning dialogue with humans while making a cup of coffee.
That demo was mind-blowing.
It really was. And of course, Tesla is pouring massive resources into their Optimus program, leveraging their self-driving vision systems for bipedal navigation.
The overarching goal of these American companies is fundamentally different from the current reality of the Unitree G1.
They aren't going for cheap and remote control.
Exactly. They are not trying to flood the market with a cheap, remote-controlled shell. They are aiming for highly premium, fully localized autonomy.
And crucially, they are leaning heavily into the security pitch.
That's their biggest advantage.
They want these machines designed, coded, and manufactured, or at the very least securely assembled within the borders of the United States.
The concept of localized autonomy is their biggest selling point against the foreign hardware.
What does localized autonomy mean in practice?
The U.S. developers point to current deployments as proof of concept. There are already American-built robots performing continuous security patrols around corporate offices today.
Like robotic security guards.
Yeah, but the critical differentiator is the data architecture. When an American-built security robot walks down a hallway, The LiDAR data it collects, the high-definition video it records, the spatial map it updates, none of that is beamed up to a public cloud.
It stays in the building.
It isn't traversing international fiber optic cables. It is routed directly to a closed on-premises server located inside that very building.
So it's an air-gapped system.
Essentially, yes. The U.S. companies are essentially selling digital peace of mind alongside the physical hardware. They are selling the guarantee that the layout of your advanced research lab isn't being uploaded to a server in Hangzhou.
But this ambition for complete domestic independence brings us directly into a massive, almost painful paradox.
Oh, the paradox is huge.
We have established the facts. The security risks of imported hardware are severe. The potential for cyber-physical danger is real. The data exfiltration threat is actively alarming the intelligence community. And U.S. companies are investing billions to build their own secure robots.
All true.
So what does this all mean? The logical, straightforward question that any observer would ask is, if it's this dangerous and we are building our own, why don't we just stop importing them entirely?
It seems like the obvious solution, doesn't it?
Why not treat them like Huawei routers or advanced semiconductors? Slap an embargo on them, ban them from entering the country, and wait the 2 or 3 years it takes for Agility, Figure, and Tesla to catch up and scale their own manufacturing. Why not just close the door?
Because we can't.
We literally can't.
The brutal reality of the global supply chain, a fact acknowledged by top industry insiders, is that the United States robotics market currently does not function without the Chinese market.
We are that dependent on them.
Yes. When an executive in the American robotics space was asked point blank if there is a day coming where the U.S. wouldn't need imported hardware or components, their answer was a flat, unequivocal no.
Wow. So if we step back and look at the whole board, we are faced with this bizarre, highly interdependent paradox.
Right.
American tech giants, fueled by billions in venture capital, are in an all-out existential sprint against foreign rivals to develop the ultimate prize, the artificial general intelligence brain, the software that can reason, learn, and act autonomously.
The Holy Grail.
But to train that incredibly advanced brain, they desperately need a physical body to interact with the real world. They need to generate petabytes of kinematic data.
They need the robots to practice.
Right. They need the physical trial and error of a robot failing to pick up a cup 10,000 times. And they absolutely cannot currently do that research at the necessary scale and at an affordable cost without relying entirely on importing the bodies built by their greatest rival.
It forces a complete reframing of how we view global technological competition. You know, we love to use the metaphor of a race.
An AI race, an arms race.
Right. The word race implies two runners on separate parallel tracks sprinting toward a finish line entirely independent of one another. If one runner trips, the other just wins faster.
But that's not what's happening here.
Not at all. In the realm of advanced humanoid robotics and physical artificial intelligence, it is not a race. It is, as observers in the space describe it, a highly complicated dance.
A complicated dance. That phrasing is so accurate because it perfectly captures the inherent tension. The U.S. and China are fierce competitors, deeply suspicious of one another's motives, terrified of espionage, and racing for economic dominance. But they are essentially holding hands while they compete.
They have to.
The staggering pace of innovation we are seeing right now, from the incredible low-cost motor efficiency of the Unitree G1 to the mind-bending reasoning capabilities of the neural networks being developed at places like MIT and OpenAI, does not happen in a vacuum.
No, it's totally intertwined.
The interdependency of the global supply chain means that in this specific moment in history, both sides actually need each other to push the boundaries of what these machines can achieve.
Let's break that down. The United States desperately needs the affordable, mass-produced physical hardware to act as a crucible for its software development.
Because we can't build the bodies fast enough or cheap enough.
Right. Conversely, the Chinese hardware manufacturers need the integration of advanced Western software ecosystems and AI models to elevate their metal shells from remote-controlled toys into truly useful autonomous tools.
Because right now, their $13,000 robot can't even open a dishwasher.
Exactly. This interdependency creates a very delicate, highly volatile geopolitical balancing act. If either partner in this dance were to suddenly break away, if the U.S. government panicked over security and banned the import of all foreign robotic hardware tomorrow,
or if the Chinese government decided to restrict the export of those machines to stunt American AI research,
the pace of innovation in humanoid robotics would instantly hit a brick wall for both nations.
everything would just stop.
They're locked together. The complicated dance requires both partners to keep moving, matching each other's steps, even while maintaining a posture of deep, fundamental distrust.
It is a phenomenal landscape to try and comprehend, especially when you think about how fast it is moving. We started this deep dive looking at a mundane warehouse in Long Island, unpacking crates of $13,000 robots that are famous on the internet for doing synchronized dances and chasing Polish boars.
The viral sensations.
We stripped away the viral hype and looked at the sobering reality of those machines. Heavy, incredibly complex, remote-controlled devices that possess zero spatial awareness will crash if asked to open a dishwasher and represent a literal physical hazard if you aren't careful around them.
The broken toe is hard to forget.
It really is. We explored the fascinating, highly tactile ways American engineers are attempting to bridge the gap between that basic hardware and advanced autonomy, using VR headsets to literally puppeteer these metal shells, generating the kinematic data required to teach an AI how gravity and friction work.
Yeah, the imitation learning.
Exactly. We didn't shy away from the darker side of this technological leap. The severe, very real fears of data exfiltration, the terrifying cyber-physical threat of a hacked 100-pound machine in your living room, and the immense difficulty of trying to create a secure black box out of imported hardware.
It's a daunting challenge.
And finally, we saw how U.S. competitors are furiously building secure, localized alternatives, even while acknowledging that the entire global market is currently locked in an unavoidable, deeply intertwined dance of supply and demand.
We are witnessing the very messy, very complicated birth of a new era. The transition from industrial robotics, the massive single-purpose machines bolted behind safety cages on factory floors, to general-purpose humanoid robots walking freely through our offices, our research labs, and eventually our homes.
It's a huge shift.
It represents one of the most significant technological leaps in human history. And the friction we are seeing right now, the intense security fears, the supply chain bottlenecks, the stark limitations of current software, these are just the sparks being generated by that massive, unprecedented leap into the unknown.
Which leaves us with an immense amount to process as we watch this industry evolve. But before we wrap up this deep dive, I want to leave you, the listener, with one final lingering thought to mull over based on everything we have unpacked today.
Yeah, this is a big one.
We spent a lot of time talking about how humans are the teachers in this dynamic. We talked about researchers putting on VR headsets, physically moving the robot's heavy limbs in compliance mode, manually showing the machine how to press down on a table or navigate a room so that the AI can absorb our human motions.
Right. The human is the instructor.
We view ourselves as the instructors, generously providing the necessary data to hollow metal shells. But consider the scale of what is happening. Thousands of these incredibly advanced sensor-packed machines, equipped with LiDAR, stereoscopic vision, and highly sensitive microphones, are continuing to operate, observe, and quietly record inside the most elite, cutting-edge U.S. labs, inside major universities, and eventually inside the intimate spaces of our own homes.
It's an unprecedented level of surveillance capability.
It really is. We have to ask ourselves, in this complicated dance, who is really learning from whom? Are American engineers just utilizing foreign hardware to build a superior software brain? Or are we, through our daily interactions, unwittingly generating the ultimate, most comprehensive physical training dataset of human behavior, human environments, and human interaction ever conceived?
That is the trillion-dollar question.
If that massive stream of kinematic and environmental data is indeed phoning home, is it possible that the true, unparalleled value of these machines is not their harmonic drives, their motors, or their cheap price tag? What if their true value is simply their quiet, constant, unblinking observation of exactly how we move, how we work, and how we live?
It definitely reframes the whole situation.
It is something to think about the next time you scroll past a viral video of a robot perfectly executing a backflip. Thank you so much for joining us on this deep dive. Keep questioning the things you see, keep exploring the mechanics of the future, and we will catch you next time.